Okay, going to talk about alkenes. Okay, so I've got a picture of, I've got ethene there. I've got just the diagram of it. And here I've tried to show the molecular orbitals. Okay, so we have got this is a sigma bond. Okay, the double bond is made up of a sigma bond. So you've got a pair of electrons in there, each one provided by one carbon. Okay, and the other pair of electrons in that bond is these are the pi electrons. So this forms the pi bond. Now, alkenes are more reactive than alkanes, more interesting than alkanes. What makes them more reactive is here you've got an area of high electron density there. Okay, because you've got 4 electrons in a small space between the 2 carbon atoms, and that means that this is very attractive to electrophiles. Now, we've come across nucleophiles before. Nucleophiles are substances which are like positive areas and tend to donate lone pairs of electrons to other atoms, whereas electrophiles is the opposite of that. They tend to be, they can be positively charged, or have a partial positive charge. And they tend to accept pairs of electrons. Okay, so let's have a look about let's have a look at a mechanism. It's not going to be nucleophilic something, it's going to be electrophilic. Okay, and it's not going to be electrophilic substitution, it's going to be electrophilic addition. That is because we're going to add something to the double bond. We're going to break the double bond, we'll add something to it. Right, so we now need to have a look at that reaction mechanism. Right, so what we're going to do is we're going to look at the reaction of ethene, between ethene and hydrogen bromide. Okay, so here's hydrogen bromide. Hydrogen bromide, of course, bromine is more electronegative than hydrogen, so it's got a partial positive charge on the bromine there, negative charge, sorry, and that means the hydrogen there has got a partial positive charge. So as this gets close to the pi bond, it will start attracting the electron density towards it. So let's just draw the pi bond there. So got the sigma bond there. I won't bother drawing that in. And here is the pi bond. Right, and then we've got our hydrogen, which is kind of denuded of negative charge. I'll try and draw that like this. Okay, hang on a minute. I'll draw it like that. So that shows you that the bromine is getting more. The bromine's got 3 lone pairs there as well. I'm not going to bother drawing them, but the bromine is getting more than its fair share of those electrons. So what the hydrogen does is it will start attracting this pi bond towards it, and eventually it will drag the pair of electrons across, and it will form a sigma bond. So that then that pair of electrons are now in this blue molecular orbital. Right, the hydrogen, of course, will then be forming too many bonds, so this will shrink back, stop being a bonding pair, and it will become a lone pair. Okay, so let's draw that. We can't draw like that all the time, so we've got to draw it with showing curly arrows. So the way we draw it with curly arrows is we draw, right, that pi bond here is going to come away onto the hydrogen and form a bond between it, yeah? And simultaneously, this bond between the hydrogen and the bromine is going to break and so shrink back and form a lone pair like that. So let's now draw the intermediate. So what we're going to have is, we're going to have this hydrogens on here. Right, now this has also got the new hydrogen on that carbon. It's got 3 hydrogens attached. And this one has still got 2 hydrogens. Now the bromine, let's think what's happened to the bromine. Well, you had a pair of electrons in there, one from the hydrogen, one for the bromine. Who gets both of them? The bromine. So that means the bromine is going to come off as Br minus. Okay, so the bromine's got a negative charge. Okay, that doesn't look quite right. That carbon is only forming 3 bonds. And also, we do our conservation of mass, conservation of charge thing. Let's think we had a neutral ethene and a neutral hydrogen bromide, and it's given us a negative bromide ion. So that means there's got to be a positive somewhere on that molecule, on that species there. Okay, let's think where the positive is going to go. Well, the positive is going to go on this carbon. It's only forming 3 bonds. That's a good little tip. If carbon's not forming enough bonds, then quite often it's going to be positive, not always, but quite often. But if you think, why is that carbon positive? Well, if you think about the double bond, okay, here, the pi bond, there's a pair of electrons in that pi bond. One came from this carbon, one from that carbon, and this carbon here gives them both away to the hydrogen to share with it. So this carbon here is going to be missing one of its electrons. It's going to be positively charged. Okay, just get rid of all that mess there. Okay, so this here is called a carbo cation. Right, cation means a positively charged ion. Obviously, that's not very stable. And what happens is, right, you have a lone pair. You've got 4 lone pairs on that bromine, haven't you? But we'll only draw one of them. That's negatively charged. It's going to be attracted towards that. So that pair of electrons goes onto the carbon there and forms a bond. And so what we've got there is the product is going to be bromoethane. Okay. That mechanism, as I say, that is electrophilic addition. So it's a bit more tricky than the nucleophilic substitution. We end up breaking a pi bond, and we add 2 molecules together to form 1 species there. That's why it's called addition. Okay, so we'll have a look at other electrophilic addition reactions in later videos. Okay.